So for problem 11a and b, we're going to be finding our derivatives of these functions, but we're told that we need to do this by using the limit definition and not our shortcut definitions of derivatives. So if this was a typical problem on a test, you might want to do that just using the quotient rule because you have a pretty simple one there. But it is likely that you're going to get at least one free response question on your test where you need to find a limit, but you have to use the theoretical definition, the limit definition of what a derivative means. So remember that that definition is the following. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is what we're going to be doing, and our function that we're using is right here, x over x plus 3. So let's see what that's going to look like. So f of x plus h means everywhere that there's an x, we plug in x plus h instead. So that's going to be x plus h divided by x plus h plus 3 on the denominator. F of x is simply our function, which is x over x plus 3. And our denominator, we have h. So far, that was just plugging in. So now it comes to the point where we have to simplify this. We can't just plug in h equals 0 yet because we're dividing by 0 here, and our entire numerator would also become 0. So we have to try to simplify this and cancel. The only way that we can simplify this is to combine these two terms on the numerator, and the only way that you can combine two fractions that are added or subtracted is by doing a common denominator. Now our denominators are x plus h plus 3 and x plus 3. Those don't have any common factors, right? You can't multiply one to get the other. So our simple way of getting common denominator is just multiply each one by what it's missing. So our common denominator is going to be x plus h plus 3 times x plus 3. And in order to do that, the first term has to be multiplied by what it's missing. And it's missing the x plus 3. So this is going to be x plus h times x plus 3. And our numerator in the second term is going to be multiplied. Now we already have x plus 3. This one needs to be multiplied by x plus h plus 3. So that's going to be x times x plus h plus 3. And our common denominator was their product, x plus h plus 3 times x plus 3. And remember that that's all over h. So this is just going from this step to this step was just getting a common denominator between these two fractions. So now we can start to expand this numerator and see what the deal is here. But first of all, in order to save some space, if we have a fraction and we're dividing by h, think of that, that's the same thing as multiplying by 1 over h. This h can actually just go in the denominator right here. And that's the same thing. And now we only have one fraction. So our next step is to simplify this numerator. So if we FOILed this out here, we would get x squared plus, so we get hx plus 3x, and then we get plus 3h. So that was just multiplying and FOILing this first combination here. And here we just distribute x. So we get minus x squared minus hx minus 3x. Again, that's all over our same denominator, which I'll rewrite here. So this step here is just expanding this numerator. But as you can see, this helps us out immensely here because we get a lot of stuff to cancel. This hx cancels with this hx, this 3x cancels with this 3x, and this x squared cancels with that x squared. So we actually get everything to cancel here except for the 3h term. So now let me write this up here. We're almost done. So our numerator now is just 3h because everything else ended up canceling out. Our denominator is the same. But you can see here, our final step before plugging in h is that we get our h's to cancel out, thus removing the problem with us plugging in 0 for h. Right? We can't plug in 0 here because it would make the denominator 0. But you can see here we can cancel an h because now h is the only thing in the numerator, so that cancels out. And finally we get the limit as h approaches 0 of 3 over x plus h plus 3 times x plus 3. So finally we can use our limit step now. We can plug in 0 for h because now it's not going to make this indeterminate. Up until this step, at any point if you had plugged in 0 for h, you would have got an indeterminate answer. Now we can do it. So all that does is if we plug in 0 for h here, this h just goes away. And you can see then the denominator term has become x plus 3 times x plus 3. So this is just 3 over x plus 3 squared. And that's going to be our derivative. You can always check your answer when you do one of these problems by just doing the derivative of this like with quotient rule. And you'll always see that it works out. But this is the limit definition, essentially the original way of how to do a derivative without your shortcut rules, is doing a limit definition, and it involves a lot of algebra and eventually being able to plug in your limit as h goes to 0. In problem number 11b, we're going to do the same thing that we did in the previous problem. We have to take a derivative by using the limit definition. And I've written the limit definition up here. Limit is f of x plus h minus f of x over h as h goes to 0. So in this problem, we need to figure out what the derivative of sine x is by using the limit definition. Now, I'm sure everybody watching this knows that the derivative of sine x is cosine x. That's something you're told to memorize in this class. But it's very possible, or very likely even, that you get a free response question on your test where you have to figure out the derivative of something using the limit definition, or the theoretical way of finding the derivative, not just using the shortcuts that you've memorized. So let's show how you can prove that the derivative of sine of x is in fact cosine of x. So what we're going to do is just use this limit, and our function is sine of x. So this is the limit as h goes to 0, and we're using sine of x now. So this is sine of x plus h minus just our function sine of x, and that's all over h. So this is what our function starts as, and we need to try to figure out how to simplify this. Obviously, we can't plug in h equals 0 right now because we would get 0 over 0 indeterminate form. So we need to figure out how to simplify this, but this is not as simple as just using algebra to get a common denominator or something, because we have two trig functions. So the only way you can simplify this is to use your trig addition angle formula for sine, because we have sine of x plus h. So I'll write that over here. Remember that the formula sine of, I'll write as a plus b for this formula. So remember that that is always equal to sine a cosine b plus cosine a sine b. That's our sine addition angle formula, and we're going to use that right here. So our a and b for this problem are x and h. So this then is the limit as h goes to 0 of, let's use this here. So this is going to be sine x cosine h plus cosine x sine h minus, we still have our sine x here, all over h. So this helps us now as we don't have any trig functions that have complicated insides. These are all just of one variable. And what we can do now is some strategic organizing of what we have remaining. So you can see here that two of these terms have a sine x, our last one and our first one. So what we want to do is group those together and factor out the sine x. So if I factor out sine x of those two terms, what would be left here is cosine of h, and then here we would have minus 1. we still have this other term. So you can see what I did here was just I put the sine x, cosine h, and the minus sine x terms together and factor out the sine x. This is still the same thing if you were to distribute this as what's up here. But the reason why I did that will become apparent in a second. The other thing that I'm going to do is, since there's one denominator term here and multiple terms in the numerator, each term here can be divided by the denominator. And what I'm going to do is split this up. I'll take this term over h and this term over h separately. Obviously, you could put these back into one fraction because they already have a common denominator. But I did this so that our trig limit identities will become more clear. So to do the final step here, we need to know what our trig limit identities are. And remember, we have these two very important ones. The limit as theta goes to 0 of sine theta over theta is equal to 1. That's one limit that you must know. The other is limit as theta goes to 0 of cosine theta minus 1 over theta is equal to 0. And as you can see here, both of these are going to be used in this problem. So in the first term, h is going to 0. That's our limit. And we have cosine h minus 1 over h. That is exactly this. So this term right here that I'm going to circle, that is equivalent to 0 for this limit. So this is 0, and 0 times anything makes it 0. So this whole term right here just disappears because it becomes 0. So now we still just have this part. But again, you can see we have one of our limits. This part that I just circled there, sine h over h. Remember, our limit is as h goes to 0. So this limit, sine h over h, is just this part here, sine theta over theta. Our limit's going to 0. That's equal to 1. So this circled part is equal to 1, which means that this entire limit just became 0 plus cosine x times 1. In other words, this is just equal to cosine x. Again, we already knew that because we knew that the derivative of sine of x is cosine of x. But this is how you prove it using the limit definition. But these two trig limit identities right here, as well as the addition angle formula for sine, those are all necessary pieces of information you would already have to know to go through these steps.
The Teaching Center, UF's Learning Resource Center.